In the previous video, you have learned about the Howie-Whelan equations. However, these two equations contain e to the power of 2 pi I as z. These are pretty cumbersome and very difficult to manipulate mathematically. So to simplify that, let's do some substitutions. Introducing two terms, we have the phi naught sub and the phi g sub, and they can be written as equations as phi naught and phi g, as well as z. Because of this mathematical treatment, when doing differentiation, a lot of things can be crossed out. The Howie-Whelan equations now takes the new form, so it's d phi g sub over dz and d phi naught sub over dz. In addition to dropping out the exponential term, also the c naught is dropped out. In both equations, we have phi g sub. By substituting one into another, we can write these two equations into a single equation. Taking one step forward, by substituting phi naught back into this single equation, we'll get another single equation in the form of second-order differential equations. This is what we get. And in this equation, there are a number of parameters. We have z, we have s, and we have c. For z and s, they are geometric parameters, so the nature of the material only enters through c. In this reformulated Howie-Whelan equation, if we can solve it, then we can predict the intensity in the directed beam because it's phi naught. Assuming it's a two-beam condition, then we can also easily calculate phi g. For second-order differential equations, the solution takes in this form. So phi naught is equal to c naught exponential 2 pi I gamma z. So d phi naught over dz can be written down as 2 pi I gamma c naught e to the power 2 pi I gamma z. Then d square phi naught divided by dz naught in the second order is equal to minus 4 pi square gamma square c naught e to the power of 2 pi I gamma z. In these equations, c naught is the amplitude, gamma is the phase. Substituting these three equations into that single equation, c naught can be crossed out and everything will be written as gamma. So it takes the form as gamma square minus s gamma minus c g to the power of minus 2 divided by 4 is equal to 0. Let's take a slightly different route. Since in a two-beam condition, phi naught and phi g are related, so phi g can be written in this form. And this can be expressed as cg. So phi g is equal to cg e to the power 2 pi I gamma z. From this, we can directly see that cg over c naught is 2 times cg times gamma. We'll see why cg over c naught is important very shortly. Coming back to the quadratic equation, we can write the solution of gamma in these two forms. And these are the two solutions to the Howie-Whelan equations. You can get some special properties when you play with gamma 1 and gamma 2. If you use gamma 1 plus gamma 2, you get S. If you use gamma 1 times gamma 2, you get minus 1 over 4 cg square. To make the equation easier to work with, we introduce another parameter called w. Coming back to cg over c naught, because cg over c naught is a function of gamma, and gamma takes two solutions, so we have cg1 over c naught 1 and cg2 over c naught 2. Substitute the solutions into these two equations, as well as expressing that in the form of w, we can rewrite these two equations into this. Now define another term called beta. We define beta in the form that w is equal to cot beta. By doing this, we placed a constraint that c naught 1 square plus Cg 1 square is equal to C naught 2 square plus Cg 2 square, which is equal to 1. Substituting this into these two equations and combine with something we learned back in high school about trigonometry, that 1 minus cos beta is equal to 2 sine square half beta, and sine beta is equal to 2 sine half beta multiplied by cos half beta. We can get the solution for C01, Cg1, C02, Cg2. And this is what we get for all the C values. Substituting the C values into the reformulated Howie-Whelan equation, focusing on the transmitted beam, we'll get something like this. Using the same substituting method, you can also get phi g, which I'm not going to write down here. Armed with this knowledge, we can write the total wave function into this format, assuming it's a two-beam condition. So A1, B1 plus A2, B2. Let me expand it slightly. Having a closer look at B1 and B2 after the expansion. So for B1, we have K1 and K1 plus G. For B2, we have K2 and K2 plus G. Each one of them is actually a block wave, which we'll discuss more in details in the next video. Rearrange the equation to group K1 and K2 together and K1 plus G, K2 plus G together. We'll have something like this. You can see that only in the second term you have G here. So the second term must be the phi G term. Here I'd like to make a special note. B1 does not represent the wave function of the transmitted beam. B2 does not represent the wave function of the diffracted beam. For B1 and the B2, each can represent the total wave function. The reason why we have B1 and B2, those two terms, is because we have gamma 1 and gamma 2 previously. Gamma is the phase of the electron wave. At the top of the TM foil, just before the beam goes into the specimen, R is equal to 0 because it hasn't gone into the specimen. Phi G is equal to 0 because there's no diffraction happening yet, and phi naught is equal to 1. Substituting R, phi G, and phi naught into the above equation, we can calculate the values of A1 and A2, and A1 is equal to cos half beta, and A2 is equal to sine half beta. We're now in the final step of solving the Howie-Whelan equation. If you recall this total wave function here, you've seen that in the previous video. So this is a two-beam condition. The phi naught term describes the transmitted beam. The phi g term describes the diffracted beam. Putting this equation together with the equation above, we can substitute the values of A1 and A2 and just calculate phi g and phi naught. This is the solution for phi g, and you can see phi g is a function of k2 minus k and k1 minus k. Since we are only considering the z component, z is either the sample thickness or how far the electron beam travels into the specimen. And from previous calculation, we know that the exponential term must have the phase 2 pi I, gamma z. Then we can write down k2 minus k and k1 minus k in terms of gamma. Then you use the Euler equation. So e to the power of I theta is equal to cos theta plus I sine theta. You put that into this equation, you can get phi g is equal to I sine beta times sine pi z delta k e pi I s z, and delta k here is equal to the absolute value of k2 minus k1. We can now write down the intensity at the bottom or the exit surface of the specimen when z is equal to the thickness of the specimen, and manipulate the equation by substituting for delta k and w. The delta k value can be written as square root w square plus 1 divided by kcg. The intensity of the diffracted beam Ig is equal to phi g square, which is equal to I square sine square beta times sine square pi z delta k e to the power 2 pi I s z. I square is minus 1. E to the power of 2 pi I s z is minus 1 as well. So the expression can be rewritten as sine square beta times sine square pi z delta k. Substituting delta k and write everything in terms of w and kcg, we'll have something like this. So introducing a new term called SF. It's the effective excitation error. It is defined as this. Substituting S effective, we finally get the phi g square equal to pi t over kcg square multiplied by sine square pi t s effective divided by pi t s effective square. And this is the final solution for the Howie-Whelan equation. To calculate the intensity of the transmitted beam is very easy. So it's just 1 minus Ig or 1 minus phi g square. This video is quite long and rather mathematical. I hope you will appreciate the process of obtaining the analytical solution for the Howie-Whelan equation. Somewhere in the video, I mentioned that the transmitted beam and the diffracted beam can be described as block waves. In the next video, I'll give you a short introduction of block waves in TEM.